squeezing with I think I don't. So, I'll be talking about our recent result on spatial squeezing with bright twin beams of light. The work has been done in University of Oklahoma in the group of Alberto Marino. I'm a postdoc in his group. So the motivation of this work was to surpass the standard quantum limit in the spatial domain by using the CCD camera. And most of you might be knowing that the standard quantum limit is the minimum noise limit possible without using any quantum source of light. And generally in noise and in any system is characterized by this, the variance normalized by the short noise. Suppose we are interested in the noise of any difference measurement, then the noise we can characterize by this ratio. This is the variance of the difference noise, and this is normalized by the short noise. And for all classical light or thermal light, it always goes greater than 1. And for the coherent states or usual laser pulse, it comes equal to 1, and that sets the standard quantum limit. And for quantum states, it goes below than 1. So, aiming to the quantum imaging and quantum metrology application, there has been done some work in the spatial quantum noise reduction in the parametric down conversion experiment. So the idea was like to look at the noise of the quantum correlated beam in the parametric down conversion, and then people have shown this short noise reduction. And as a proof of principle, they have shown like you can resolve the object, you can resolve the image of a center object with a better signal to noise ratio that with the quantum correlated light that is possible with the classical light. So, but the problem with those kind of experiments the limitations are basically the photon pair generated with the SPDC process are quite faint. So your signal to noise ratio is limited by 1 by root n scaling of the short noise. So, and other problem with those kind of experiment is like the photons pair are quite broadband. So if you want to use those photon pair for light atom based quantum protocols, then you need to have like spectral filtering. Without a spectral filtering, you can't use those. So to overcome all these limitations, we demonstrate the sub-short noise quantum correlation or sub-short noise quantum reduction with the bright twin mix of light generated with the four-way mixing experiment. So as a quantum correlated beam, we are using the four-way mixing, and four-way mixing is a chi-3 nonlinear process that involves the interaction of 4 electromagnetic waves. Basically, we are using rubidium vapor cell. So what happens, your 2 pump photons are being absorbed in the rubidium atomic vapor cell, and 2 quantum correlated beam called probe and conjugate are generated through the chi-3 nonlinear interaction. So as in all universal phenomena, energy and momentum has to be conserved. In this process, the energy conservation decides the frequency of the probe and conjugate beam, and the momentum conservation decides the direction of the generated probe and conjugate beam, basically wave vector of the probe and conjugate beam. So they are the momentum correlation. And these momentum correlation of the four-way mixing photon pairs leads to the spatial correlation in the far field. So another important point in those kind of experiments is the coherence area. So in case of real experiment, we are using the Gaussian laser beam, which have like finite angular spread in their wave vector. Due to having the finite angular spread in their wave vector, there will be the uncertainty region or uncertainty in the wave vector of probe and conjugate beam. So that uncertainty region sets a minimum correlation area of the probe and conjugate beam, and that we call the coherence area of the probe and conjugate. So now coming to our experimental setup. So basically our experiment consists of 3 main parts: the laser beam, rubidium vapor cell, and EMCCD camera. So we interact pump beam and a weak probe beam inside the rubidium cell, and we generate the bright quantum correlated beam called probe and conjugate. And to generate those bright beams, we are seeding the probe beam. There is a fainter beam which is being used for the seeding process. And these quantum correlated beams have the momentum correlation, their momentum correlation can be mapped to the spatial correlation by using a lens system in each of the parts. Basically, we are looking at the far field at the EMCCD plane. But another problem with, or the complication in those kind of experiments is, as we are seeding the process to generate bright quantum correlated beam, that means we are introducing some noise, or as we are interested in the quantum noise, so we have to reduce or we have to eliminate the classical noise introduced by the seed beam as much as possible. So for that, we are using some mode called kinetic mode of EMCCD camera. So what we are doing basically, we are dividing CCD sensor into 2 frames, and at a particular time, we are exposing only 1 frame of the CCD camera, and the acquisition of CCD camera is synchronized with the probe or pulses. And once we expose a particular portion of the sensor, we can transfer the charge stored in that frame with a very fast rate of like 300 nanoseconds per row. And like in the 60 microseconds, we can shift the charge from the first frame, and we can fill the another frame also. So we can get like 2 images of the probe and conjugate beam in a very fast time scale. So this acquisition of the frames in very fast time scale allows to subtraction of the DC. But if we subtract these 2, then this allows to subtract the low frequency classical noise as well as the Gaussian profile. Now we get like probe noise and conjugate noise, and that's what we are interested in. So next, what we do, coming to the experimental results, so we first analyze the coherence area of our beams, like minimum correlation scale of the beam. So what we do, so this is the conjugate noise, this is the probe noise. We crop a small section of the probe conjugate noise and look at the cross correlation of that noise with the other beam. Like we scan over whole of other beam and then look at the cross correlation profile. And it comes out like this. It is peak correlation, and that peak indicates that there is a maximum correlation between the cropped region of the probe with somewhere in the conjugate. And it has some peak profile, and the width of this profile tells us about the extent or about the scale of the coherence area or correlation area of the beam. So we tested this with the usual coherent pulses, which don't have any, or they don't, in the coherent state, they don't have any correlation, and we were not expecting any correlation, and there's like a smooth surface without any correlation peak. So finally, coming to the results of the noise ratio, which I talked about the first slide. So we are interested in the noise reduction. So what we are doing, we have already got like probe noise and conjugate noise. So we subtract these 2 and get the noise of our measurement. And then we quantify the noise of our measurement by this ratio, is called noise ratio. And other important thing is, as our detection area is limited, or minimum detection area is limited by the pixel of the CCD camera, which is like 16 micron in our case. So, but to have like noise reduction in the difference measurement, we have to cover at least 1 coherence area, that is the minimum spatial scale of the correlation. So for that, we are using the feature binning of the pixels. Basically, we are grouping many pixels and then looking at the noise of those pixels. That's called the binning. And other thing is, like due to phase matching condition, the correlated region of probe and conjugate are diametrically opposite. So to have like noise reduction, the difference noise, we rotate one of the image by 180 degree and then subtract the noise. So the results are those. So you could see that the blue one shows is the flip after rotating the image and then subtracting. You can see that our noise in those measurements goes significantly below than 1. That is, we are in the quantum domain. But if we don't flip either of the beam, then we will get the excess noise. That is because when we don't flip either of the beam, then we are taking the difference of the uncorrelated region. As you know, the noise always acts in quadrature. That's why we are getting the excess noise. And the error bar in those plots indicate the spread of data over 100 measurements. So we have taken 100 measurements, and the spread tells about the you can see like in the 100, even in 100 measurements, we are quite below and the short noise limit. And at the last, we test those analysis with the coherent pulses, and as we are expecting, and we talked in the first slide, we are always get the short noise limit, and it's like 1 we have got. And finally, we can say that we have experimentally demonstrated the sub-short-range quantum spatial correlation using bright twin beams of light, which may have a lot of application in the quantum metrology and quantum application. And we have shown like spatial squeezing of around 2 dB. Thank you very much.